oh so still. Shh, shh, you're all alone. Shh, shh, and so peaceful until you fall in love. Simple, the sky up above. Simple is caving in. Wow, wow! You've never been so nuts about a guy you wanna love. You wanna cry, you cross your heart and hope to die till it's over. And then shh, shh, it's nice and quiet. Shh, shh, but soon again, shh, shh, starts another big riot. You blow a fuse, sing boom, the devil cuts loose. Sing boom, so what's the use? Wow, wow, of falling in love. It's oh so quiet. It's oh so still. You're all alone, and so peaceful until you ring the bell, big bell, you shout and you yell, how you broke the spell. This is where you almost have a fit. This guy's coach and I got hit. There's no mistake. This is it. Till it's over, and then it's nice and quiet. Shh, shh, but soon again, shh, starts another big riot. You blow a fuse, sing boom, the devil cuts loose. Sing boom, so what's the use? Wow, wow, of falling in love. The sky keeps in, the devil cuts loose. You blow, 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 blow your fuse. Ah, when you fall in love.
All right, so continuing with where we left off yesterday, remember we were doing the basic CRUD operations in a binary search tree. We'd already done the search, the insert, and most of the delete. What we left off here was deleting when in the instance where there are both children there. So for example, if we were to delete 40 right here, right? Then what we need to do is we need to go to the left subtree and find the maximum value, 28, and then promote that up to be the new root of that subtree right there. Consequently, we have to get rid of that 28 that we just promoted. And so what we've done so far is we've found that maximum node. The element that we're trying to delete, right? We go to the left child, and then we get the maximum node of that subtree. Now what we need to do is promote the maximum node's value to delete, and then delete the maximum node. And that's going to actually be pretty easy here, because all we need to do is pull out the element, right, and set, let's see, toDelete.set element, right, to max node.get element. Right? All we're doing is replacing that element. Now, if you remember, when we originally designed this tree node class, we initially designed it so that it was immutable in its element. We made that final so that you couldn't change it. Generally, that's the way that you want to go. You want to make things private, you want to make them final, unless you have a very good reason to do otherwise. And we had a very good reason for the parent left and right because we wanted to change the topology, the structure of that tree, and we wanted to be able to manipulate that tree. And now, at this point, I have a very good reason for changing the element as well. So what we'll do is we'll take it and make it not final so that we can change it. And then where's my get element? I'm going to go ahead and generate another method here called set element that takes an element of type T, element, and sets this dot element equal to that element that you give me, right? All right, so we've changed our design based on new information here, right? We refactored our design, we've changed it. And now we can actually set that element, okay? Now let's go ahead and delete the max node, right? This max node right here, we've already got it, so I want to delete it, right? How do we go about doing that? Don't we have a function to do it? This function? So let's go ahead and call this function, this dot delete. And what we'll do is we'll delete max node dot get element, whatever element is contained in there. Be careful here though. Look at the ordering of these. So I set the parent that element to the max node's value, and then I try to delete it. Let's try to do that over here visually. What ends up happening is I end up deleting 40 right here. Let's change color over here. I end up deleting 40, and I end up putting 28 in its place. And now this max node down here that I want to delete, now I need to delete it. But be careful. I've got an intermediate state here where I've got two 28s. Which one are we going to end up deleting? Probably this one right here. Right? And then we would go and we'd find the maximum element, replace it, then want to delete 28 again, but guess what? This is still 28. So we would find the maximum element to delete it, right? And we're going to get stuck in an infinite loop here. Let's go ahead and try it. All right? Let's go ahead and go over here to the demo. And remember, we've got this large binary search tree. Let's go ahead and try to delete, what was it, 40 that we were trying to delete? And we're going to get stuck in a infinite loop of calling, infinite recursion here, I think. Right? There we go. Indeed, we got into an infinite loop, which gives us a stack overflow. All right, back to the drawing board over here. These are the two operations that I want to do, but I don't necessarily want to do them in that order. Let me go ahead and move this up here. Right? Delete the maximum node, right, from the tree itself. Right? Now what that ends up doing, let me go ahead and reverse all this. Right? What that ends up doing is it ends up saving 28 over here because we do have a reference to that node now. But then we end up deleting it. Right? We don't have a duplicate right now. Instead, we just end up deleting this node right here. Right, there we go. Come on. There, it's gone now. Right? And now at this point, what I can do is I can take this, the element stored in here and then place it in this node up here, giving me 28. Now it should work, right? Because I have I've switched the ordering of those. Something else that I could have done is I could have saved off the element itself, right? And then deleted the maximum node because there'd only be one copy, and then set the element later on, right? So let's go ahead and see if this works now. I'll go ahead and get rid of tree node. And can we delete 40? I have no idea, right? Remember how we were testing this? We were visually testing this. In fact, this is what many of you are doing with your project right now. You are visually testing your output, right? Does it match? Does that match? And this is how we grade it too, right? If you're not doing formal unit testing, you're doing visual verification. That's what we want to see in your design documents, right? Beyond the JUnit test that you might have written and that you might have run, we want to know how did everything pass? Yes. How did they pass? How do you know that they passed? Well, I looked at the expected output and I looked at my output and they matched, right? Visual inspection, right? That is a valid testing technique. It's not the greatest one, but it is valid, right? All right, so remember that here, let me go ahead and get rid of that. Let's come back over here and let's go ahead and test this now visually, right? I want to test, say, deleting 40, and then that'll mean that, 20, and then let's go ahead and delete 20, or no, let's do 50 next, right? 50, so 1, 2, and then 3. I don't know if 20 will end up having 2 children or not, but let's see if it works. So 40, 50, and then 20. Right? So 40, then 50, then 20. Right? And what I'm going to do in this case is I'm going to print it out each and every single time so that I have a snapshot of what it looks like, then what it looks like, and then what it looks like. Right? Let's go ahead and run that again. Select everything, bring it over here to Overleaf, recompile, and see if it worked. Now remember that we were doing 40, 50, 20. So let's start way over here. If I were to delete 40, remember that 40 is over here, then that means that 24 gets promoted up in its place, right? Right? Yeah. So, oh no, 28. Oh, that's right. I erased it. There we go. I'll restore it. There we go. Right. So 28 gets promoted up into its place, and then 28 gets lost, right? It's that right's child. Then we delete 50 right at the top, right? That means that what should end up taking its place? 49, right? 49 comes up here, and we don't lose that 48 that's hanging off of 49, right? So that's good. Now we're going to delete 20. It means that I come over here to promote 15 up here, and then 12 is preserved as the right child of 10, and indeed it is. Right? So a nice little way of testing this visually. Okay. There are a couple of things that we didn't do here. One of them we'll do, and the other one I'll save off and let you do it as an exercise. To do, right? Fix all parent references. The entire time what we were doing is we were fixing the left and the right child, right? But remember when we promote this up, right? Or let's say when we delete 24 right here, right? That means that we set the right child of 20 to be 28. But we never actually reset the parent of 28 to be 20. Right? So I'll leave that as an exercise for you to do. As long as you're only going down in the tree, it should be okay. But if you ever need to go up in the tree, right, say to determine the depth of a node, then you need those parent references fixed. So I'll leave that as a to-do. But the other to-do we will do, right? Consider the case, the corner case, of deleting a single node root. So let's go ahead and try it out first. And the way that I'm going to try that out is by creating a binary search tree. And let's go ahead and get rid of all of this, right? And add, say, bst add 50, and then immediately try to delete it. Bst dot remove or delete 50, right? Now this is probably not going to work. Even though I already tested the corner case of adding it to an initially empty tree, what happens when we end up with an empty tree at the end, right? Why does it end up being null, right? So can you set the right child of this? Basically what we were doing this entire time is, it is a leaf, right? Can you get the parent of a single node tree? No. So let's go ahead and treat this as a corner case. If it is a single node tree, this is a single node tree, then we will take care of it here. And what I want to do, first of all, how do I determine if it's a single node tree? This dot size is equal to 1. All right. By the way, did we take care of size down here? Oopsies. All right. Did we take care of the size? Nope. This dot size minus minus. Right. I'm going to steal that code because we're going to do the same thing up here. Right. How do I make this into an empty tree if it's a single node tree? This dot root is equal to null, right? And then decrease the size, or just set the size now that you know what the size is. This dot size is equal to 0, right? And return, because you do not want to do the rest of this stuff down here, right? You are done at that point. I should have actually saved it off, right? Let's see. T result is equal to this dot root dot get element. And then I will end up returning the result because we end up returning what we delete. Okay. Let's try it again over here. And no news is good news, so it probably passes. I'm not going to bother printing it out, though. Right? All right. In fact, that looks like what happens with my Tixie here, right? It ends up printing out an empty string because it's empty, right? If you want to, you can go ahead and say empty, right? There we go. And it'll print empty now. Okay. All right, that's binary search trees, right? So there's still a problem here, right? That we have not actually solved our original problem, where we want a general purpose data structure that gives us efficient operations for everything, right? And that's why we're going to introduce our last data structure here called a heap. You might have already been familiar with heaps as far as memory allocation goes, but these heaps are going to be a little bit different. Binary search trees are not necessarily balanced. Remember, they can be skewed all the way to the right, right? BSTs might have a depth that is linear, right? Which kills the efficiency of all of our operations, because now adding something, removing something, and retrieving something are all now order n because they're proportional to the depth, right? And that happens if you've got kind of a skewed linked list kind of thing, right? One solution that we will not cover, but I'll briefly mention, is to use what's called a balanced binary search tree. And there are dozens of these things: AVL trees, red-black trees, 2-3 trees, et cetera, and they all guarantee that the depth is going to be logarithmic. The way that they do that, I'll really quickly show you here, is suppose that you have a skewed tree. So here's 10, 20, and 30. It's skewed all the way to the right. What you do is you rebalance it, right? So this is my imaginary hill here, right? And what I'm going to do is I'm going to take a chain and I'm going to yank it down onto the other side of the hill. Right? Now note that this is a binary search tree. Everything over here is greater than 20, or 10, excuse me. 30 is greater than 20. So what ends up happening when you do this is that you end up rebalancing it. 20 comes up to the new root, and 10 and 30, 10 is on the other side of it, and 30 is over here. Right? That is called a rotation. Right? And there are actually 3 other rotations, and I'm not going to get into it, but you have, what if it's skewed to the left? Then you do the rotation, but a mirror. What if it's skewed zigzaggy? Well, then you do a rotation here and a rotation here. And there are a whole bunch of other details that are necessary to cover it. Those are called AVL trees. 2-3 trees are a specific type of B trees, and B trees are used in databases to store stuff. This is why efficient retrieval is, or why retrieval is efficient in a database, because it stores it in a balanced binary search tree kind of structure. And it's also why it's important to put keys and indices on anything that you're searching for in a database, because then it will store them in these efficient data structures for fast retrieval. If you don't do that, then you go back to plain old linear search here. Okay? Anyway, that's not going to be our solution. Our solution is going to be a half measure called a heap data structure. What visualization comes to mind when you think of a heap? A heap of what? Heap of garbage, right? A heap of your clothes, right? When you have a heap, right, and where do you throw? So you've got a heap of garbage. Where do you throw the next thing? You throw it on the top of the heap, right? But does it end up being at the top? Nope. It could trickle down. Maybe it does. You got lucky and it stays up there, but otherwise it trickles down until it settles. Maybe it comes all the way down. Maybe it goes halfway or something like that. And that's why we call it a heap data structure. It's going to be a pile, right? Somewhat disorganized pile of stuff. But it's going to have very, very nice properties. The first property is that it's going to be full. Right? Every child is present at every level except for possibly the last deepest level. And in that case, they're full to the left. So you're going to have a picture that looks something like this. Everything exists up to the second to last level. Then at that last level, everything is going to be full up until the left. Right? In other words, there are not going to be any gaps in this tree. Right? The only gaps are down here at the lowest level and all the way to the right. Right? That is going to give us our logarithmic depth. That's going to give us our guarantee on the logarithmic depth. Then the second property that it satisfies is the heap property. The key of every node is less than both of its children. This is called a min heap. You can, of course, flip this and say that it's greater than both of its children, and you'll have a max heap. But let's focus on min heaps for now. Okay? So, for example, if I've got a key k here, and it's got 2 children, then it's going to be greater than k and greater than k. That's the only thing that you can say. You can't say that this is going to be less and this is going to be greater, because that's a binary search tree. All right, so let's take a look at an actual example. Here is a min heap. Here we go. There we go. All right. Look at each one of these nodes. 1, it is less than both of its children, 5 and 30. It just happens to be that the lesser of the 2 children is to the left and the greater is to the right, but that doesn't always have to be the case, right? Looks like I might have, no, I didn't do that here. 55 is less than 72 and 70. But 72 is greater than 70, right? So it's a little bit less organized than, say, a stack or a binary search tree. You only have this heap property. All right, and by the way, it's full to the left, right? This would not be a heap. If I hang another node off of here, I would have a huge gap right here, and that's not a heap. That would not satisfy the fullness property, right? So it is full at every level, right? 2, 4, 8, except for the last one, and there it's going to be full to the left. Okay. Make a couple of observations about this. Right? First of all, can you search this tree efficiently like a binary search tree? No, because I want to find, I don't know, 60, right? If I'm just starting at the root here, do I know that it's in the left or the right? I have no idea, right? I could say, well, maybe it's in the left, but then what if you're searching for 45, right? 45 is even less than 60, and so maybe you'll go left, right? Nope. So you end up having to do a full a BFS or a pre-order traversal or something like that in order to find what you're looking for. Meaning that you're going to potentially look at every single node, order n. Okay? That's my first observation. What's my second observation? What's at the very top of this heap? 1, but in general it's what? The smallest value, the minimum element. So those are two great observations, right? This is not a general purpose data structure. Searching would require order n, right? So we're not there, but we do have access to the minimum element. The minimum element is always at the root. How can we exploit that structure? My third observation is what I've already observed before. The fullness property guarantees that the depth is logarithmic. So if we can come up with some alternative operations that are going to be proportional to the depth, then they end up being efficient, log n. Okay? What are those two basic operations? Okay? What they're going to be are get and remove the minimum element, and the second one is going to be add an element. Right? Those two operations, that's it. In other words, it's a restricted access data structure, right? This ends up being a restricted access data structure. Just like a queue or a stack. It's efficient as long as you use it in a particular manner, right? If you only insert and delete at one end, insert and delete at the other end, and you don't go arbitrarily searching for something or arbitrarily trying to insert or remove something, then everything is going to be efficient. And in this case, these two operations are going to be efficient. Let's describe how they work. All right? Let's go ahead and do the first one first. Get and remove the minimum element. All right? So first of all, I'm going to save off the root element to return it. How are we going to take care of it now? Right, so let me do that. What I'm going to do is I'm going to save off 1 over here. Here's min is equal to 1. That'll be my result that I send back to the calling function. But I've now deleted it. Okay? My first instinct is to immediately go to the children because this is, I only know binary search trees up to this point. And so I only know that I can start at the root and I can go down to the left or the right and I don't know, which one should I promote? Oh, 5 or 30. What if I put 30 up here? Is that going to, that violates immediately the heap property because 5 is less than 30. It should be up there. Okay, fine. Then we're going to follow that pattern of promoting up the smallest child. Right? That means that we have to take care of 5 now. All right? What do we do? Well, the smallest child here is 50. Oops. 50. So I'll promote that up. But now I need to take care of 50. And if I promote the smallest child up now, what is it? 53. What happens here? It ends up being a gap, right? The fullness property is no longer satisfied. Remember, the fullness property is that every single node is present up to and including the second to last level, and then the last one is full and to the left. but now it's not, okay? So back it up, that's not going to work. Right? Let's instead ensure that the fullness property is satisfied first. If I ensure that the fullness property is satisfied, right, then which one should I promote up? The very last one. Right? And if I do that, then the fullness property is indeed satisfied. 63 comes up here, and now 63 is gone entirely as a node. There we go. There, it's gone. Okay? Is the fullness property satisfied? Yes. But is the heap property satisfied? No. This gives me an opportunity now to do what's called heapify. Now I exchange it with one of its two children, right? The minimum child. In this case, that's going to be 5. I'm going to change this so that it's 5 now. And then I put 63 down here. Okay? Is the fullness property is still satisfied? It was satisfied from my very first operation. But now is the heap property satisfied? No, because 63 is greater than both of its children. So what I'll do is, yet again, I will swap, right? And now 63 becomes 50, and 63 is now down here. Okay? The heap property is still not satisfied, so I end up swapping it with its child, a minimum child. 53 comes up here, and now 63 is down here. Is the heap property now satisfied? Yes. Right? How many times did I have to compare and swap? Right? 1, 2, 3, and then I would have fallen off the edge because there are no children here. Right? So it's proportional to the depth. Right? And that is how you heapify it, and you fix the heap. Right? So you replace the root element with the last element, right? We mean by last element, the element at the lowest level all the way to the right, if you can find it. Right? That assumes that you can find it, right? And then you heapify it, right? You fix the heap property. Oops, sorry. Heapify. Right? Heapify or fix the heap, some people call it one way or some people call it the other way. You swap the element, starting with the root, with the minimum of its left or right child until either the heap property is now satisfied or you reach a leaf node, in which case you're done. Right? If it hadn't been 5 instead, if it had been like 73 or something, then I would have promoted up 30 and then 40, and then I guess it would have still gone all the way down there. But you could end up throwing something on top of the heap, and then it trickles down to the middle element instead. Okay? Just like that heap of garbage. You throw something on top, there's no predicting on where it ends up. Okay? Now this is going to be order log n. Why? Because we have that fullness property that guarantees that the depth is going to be logarithmic. Right? This, of course, again, assumes that you have free or efficient access to the last node. Do I? If it's a tree data structure? Can I immediately jump to that oops, that's not what I wanted. Can I immediately jump to that last element there? Right. At least if it's stored as a tree, I don't see a way of doing it. But that's the idea. We'll talk about how that's done efficiently here in a second. Let's take care of the next one, add an element. Right? So once again, you are going to preserve the fullness property first. Right? So preserve the fullness property first. Right? And the way that we're going to do that is by adding the new element to the last spot. Right? That is the next available slot at the deepest level all the way to the left. All the way to the left. Okay? Way to the left. So over here, if I want to insert, I don't know, something that's not already in here, 42. Insert 42. Okay? The next available slot is going to be the left child of 53. And that's where I'll end up putting 42. Okay? The fullness property is satisfied, but is the heap property satisfied? Nope. So what you do now is a process of heapify or fixing the heap, but you do it from the bottom up. Right? So what I need to do now is I need to look at its parent and say, nope, that violates it. So what I'll do is I'll swap it. Swap. And 53 comes down here, and 42 comes up there. You continue until the property is satisfied. So I need to swap these two, and this ends up being 50, and this ends up being 42. Do I continue up to 5? No, because 5 is already less than 42. So in this case, I only had to go up half of the depth. Sometimes if I were to insert, for example, -1, right? Insert -1 here, it would end up traveling up all the way to the top because that's the new minimum value, right? So that's the idea, okay? You insert it as the last element, all the way to the left. You swap it, you iteratively swap it with its parent all the way up the tree until either the heap property is satisfied or you reach the root. Once again, this is going to be order D, which because of the fullness property is going to be order log n, right? Because you only have to go up to the top. But once again, this assumes that you have free access to the next available slot. Right? And with a tree data structure, or at least with the way that we've been representing trees, I don't have that necessarily. So instead what we're going to do is we're going to talk about an alternative implementation. Implementation, right? Okay. And to do that, I'm going to visualize it over here. All right, so what if I were to read this left to right? Okay. So if I were to read this 1, 5, 30, right? 50, 55, 40, 80, right? So let's write that down. 1, 5, 30, right? 50, 55, 40, 80, 60, 53, 72. That's as far as I'm going to go. Okay? Now, what if I read it left to right? What kind of ordering was that, by the way? That's not a pre-order traversal. It's not in order. What was that other one that we talked about? Where we read it top to bottom, left to right? That's called BFS. Stands for breadth first search, right? Right? So if we read this in a breadth first search manner, I could put it into an array, okay? So what I'll do is I'll start out at index 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, ... on both of these, okay? Now let's make an observation. 1 is at index 1, right? That's just a coincidence. Where is its left child and where is its right child? Right? So its left child is right next door at 2. Where is its right child? Right next door to it at 3. Right? What about, say, 50? Where is its left child? Where is 50 and where is its left child and right child? So where's 50? Right here at index 4. And if I were to search over for 60, it's going to be at index 8. And its right child is at index 9. Right next door to it. Can we start to see a pattern here? What about 5? Index 5 here, 55, right? So where's its left child? It's at 10, right? So 5 jumps to 10. And I didn't write it, but where would its right child end up being? Right next door at 11, right? So what's the pattern? If I were to say that I have a node U at index I up here, right? Where is its left child and where is its right child? What index would the left child be at? 2i. Right? And if the right child is right next door, it'd be at 2i plus 1. By the way, where would the parent be? So the parent is at index, say, j. Then that means that this one is either at 2j or 2j plus 1. So how do I go back to j? I divide by 2. And I take the floor of that. Because if it's at index, say, 11, right, then where is its parent? Traveling back over here at 5. It's 11 divided by 2, but that's 5.5. You floor it, and you're at 5. Right? And so that's how you do it. It's a nice little neat trick. Right? I've got it. There we go. here's how you can represent a heap with an array. If you've got a node U and it's at index I, its left child is simply at 2i, and right child is at 2i plus 1. And then to go back up to the parent, it's just another index calculation here. And because it's all in an array, we have random access. I can jump from index I to index 2i easily. Now do we know how we can get access to the last element and the next available element? Right? So again, the implementation is use a basic array. Right? Ignore index 0. Right? And then each element stored at index I has a left child at 2i, right? And right child at 2i plus 1. Right? Parent at floor of, can I do that in this LaTeX? Floor of frac 2i. No, I can't. Is it L floor then? There we go. That's the LaTeX. And then it's R floor. And then balance those out. There we go. 2i, I divided by 2 floor of that. Okay? All right. Random access means you can walk along the tree efficiently. Keeping track of the size means you have access to the last element at index. Suppose that we have size, say, n, right? Where would the last element be? At what index? If you keep track of the size. If I've got 5 elements in there, right? Remember, I burned 0 already. So 0, 0, 1, 2, 3, 4, 5. It would be at index n in general. And the next available spot, which is going to be index equal to n plus 1. So as long as you're keeping track of the size, you have free access to this using random access. Okay? What about applications? Right. One application is an efficient priority queue. Priority queue. Remember, we explored that idea when we looked at queues, and we said that some people might have VIP access, right? An efficient priority queue would mean that, say that this thing up here has the highest priority. The lowest number has the highest priority. So the next thing to come out of this data structure is the one with the highest priority. Then it fixes itself. So that the next thing, say 5, right? That's the next thing out because now it has the next highest priority. You want to be able to add something to the line, to the queue, right? Well, you don't necessarily want to add it to the next line, right? Instead, it'll trickle down here to where it belongs somewhere. And it'll come out of the queue in its next available, or in its proper priority, right? So it's an efficient priority queue. The other one is sorting. Right? What if I were to put stuff into this array, into this heap, and then progressively take it out? What order would they come out in? 1, 5, 30, then what? 40, 50, 55, 80, right? Sorry, 53, there, we've got some other 50s in there. Actually, we've got some other 45s there too, right? So that's called heap sort. Let's actually implement it over here. I'm not going to implement a heap here. Instead, what I'm going to use Java's heap, which is a priority queue, right? Of, say, integers. Right? PQ is equal to new priority queue. Right? Let's go ahead and import that. If you want to, you can take a look at what it looks like. Let's see. It is indeed where is it? An array implementation. Right? It keeps track of its size. Right? So this is exactly the implementation I was just talking about here. By the way, you can do it as a tree, and you can do it efficiently. If you're interested, all you have to do is do some clever math. And if you're interested in that, it is in the book. Right? Otherwise, what I'm going to do is I'm going to add elements to this priority queue. pq.add, I don't know, 10. pq.add 50. pq.add 40. pq.add 30. Right? pq.add 20. Right? I'm just putting stuff in. Now what I'm going to do is I'm going to take stuff out. While PQ dot is empty, while it's not empty, while it's not empty, I'm going to take stuff out. System.out.println PQ dot, what is it? I think it's poll in this case because it's acting as a priority queue. So it makes sense that it's poll because that was the dequeue operation for queues, right? Now what order are they going to come out in? 10, 20, 30, 40, 50. This is called heap sort, right? And we can write it up really quick here, right? Because it exemplifies the conclusion of this course. Here's my heap sort algorithm, right? I'm going to create initially init a min heap, right? Now for each element a sub I in a, which is our input. I didn't write that, but you can imagine what it will look like. What I'll do is I'll insert or add a sub I to the heap. Put stuff in, simple for loop. While h is not empty, output h dot get min, get and remove min, right? And that's it. 4 lines of code. Put stuff in, take stuff out. I would characterize this as dumb code. Dumb code as in it's straightforward code. What we have working for us and doing all the heavy lifting is that smart data structure. Now remember, at the very beginning I shared a quote with you from Eric S. Raymond about what the theme of this course was. Dumb code and smart data structures are a lot better than the other way around, right? And think about, say, merge sort or quick sort. Clever code, that's not dumb at all. No data structure, you just have an array, right? Wow, that is so much simpler, right? Put stuff in, take stuff out. Now, of course, you do have to realize that it also has to be efficient. So I'll give you the really quick rundown of this. Let's look at an iteration. Let's look at the insert phase, iteration 1, 2, 3, 4, 5, n, because we're inserting n things here. What is the size of the heap? Well, it progressively gets bigger. On the first iteration, there's nothing. On the next iteration, there's 1 element in there. On the third iteration, there's 2 elements in there, and I'm inserting the third element. Then I'm inserting the 4th element into, then there are 3 already in there. 3, 4, n minus 1. Right? Now remember that this is going to be efficient with respect to the size of the heap. Right? Everything is going to be log n, where n is the size of the heap, not the array that you're trying to put stuff into. So, number of comparisons, comps / swaps. Right? That's going to be, well, 0, because you're not doing anything. But otherwise then log 1, log 2, log 3, ... Down at the end it's log n minus 1. So what is the grand total of all of these? Okay. What is the summation of I running from 1 up to n minus 1 of log of I? Right? Log of 1 plus log of 2 plus log of 3 plus ... plus log of n minus 1. Right? Now you're going to have to pull out your high school log identities. Right? What happens when you have log of A plus log of B? That's equal to log of AB. Well, you can do that n times. And what do you end up with? Log of 1 times 2 times 3 times ... times n minus 1. Right? What is this right here? N minus 1 factorial. Right? Also called the gamma function, n minus 1 factorial. Now remember, factorials are big. But if you take the log of something that's big, it makes it manageable. Right? I don't like that minus 1, so let's go ahead and just set up a upper bound here. Log of n factorial. Okay? I think we did this one when we looked at big O analysis. If you replaced each one of these terms with the largest term, I'll just go ahead and replace this term with n, replace the next term with n, replace 1 with n, and I'm just making it bigger, right? Okay? Then this is less than or equal to log of n to the n. There's another thing called Stirling's approximation that you could use, but we won't go that far because this is enough. Now pull out another log identity. A to the k. What happens to that k? It comes out front. And we have what? N log n. We've matched our efficiency with respect to merge sort, tim sort, quick sort. Right? But we've done it all with a really, really nice, smart data structure. And by the way, if you're concerned about the other phase here, while H is not empty, you have to pull stuff out. Guess what? It's the exact same thing here, except that instead of n, it's n and then n minus 1, n minus 2, dot, 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 until it gets down to 0. So you're summing all of these up, meaning that this ends up being 2n log n, but we ignore those constants. And this is going to end up being order n log n. Right? But how much nicer is this? Right? Dumb code, smart data structure. Now, one of the takeaway, we'll have a course conclusion on Monday. Remember, there is no class on Friday, so that you can go over to the senior design showcase later in the day. But otherwise, I mean, this exemplifies this course. The questions that you should ask yourself after you're done with this course are, how do I model stuff using objects? What data structure could I pull off the shelf? A heap, a stack, a queue, a binary search tree. What could I pull off the shelf to make this easy? To make this trivial, like this, with dumb code. Put stuff in, take stuff out. A heap sorts it for me, right? Just by the way that I put stuff in, right? By the nature of the heap itself, okay? All right, so we will meet on Monday for the last time. We probably won't meet on Wednesday or Friday unless we want to give you more time to, if you want to, resubmit your one assignment. Remember, take a look at the campus wire for the details if you're going to do that, to try to improve your grade if you messed up one of the assignments. But otherwise, we will meet on Monday.